It is 1942, on the floor of an American war plant, and a young woman is standing at a machine. A year ago, she had never seen the inside of a factory. She was a school teacher, or a housewife, or a shop clerk, and she had never operated anything more complicated than a sewing machine. She has had, at most, a few weeks of training. And now she is producing, at this machine, a precision metal part, a part that must be accurate to within a few thousandths of an inch, a part that will go into an aircraft engine, or a machine gun, or a tank transmission, a part that must be so perfectly identical to the tens of thousands of others being made just like it that any one of them will drop into any engine, anywhere, and fit. She loads a rough piece of metal into the machine. She pulls a lever. The machine does its work. She removes a finished part, drops it in a bin, checks it against a small steel gauge, and loads the next piece. Every 30 seconds, another perfect part, hour after hour. And she could not, if you asked her, tell you the first thing about the theory of machining. She does not need to. The machine and the tooling around it are doing the thinking. All she does is load, pull, unload, check, multiply that woman by millions, multiply her machine by hundreds of thousands. This was the reality of American war production, an ocean of interchangeable parts, produced to fantastic precision in unimaginable quantities by a workforce that was overwhelmingly new, untrained, and unskilled. And here is the puzzle that should stop you. Today, when we make millions of identical precision parts, we do it with computer-controlled machines, CNC machines, which read a digital program and position their cutting tools automatically to tolerances finer than a human hair, guided by a computer. In 1942, there were no computers on the factory floor. There was no CNC. The numerically controlled machine tool would not even be invented for another 7 years, and would not be practical for years after that. So how did America do it? How did a factory full of people who had never machined anything in their lives produce the tens of millions of perfectly interchangeable precision parts that the war demanded, without a single computer to guide the machines? The answer is one of the deepest and least understood triumphs of American industry, and it comes down to a single, powerful idea. If you cannot put the skill in the worker, you put the skill in the tool. To understand the magnitude of what America accomplished, you first have to understand what a CNC machine actually does, because that reveals exactly what problem the wartime factories had to solve without it. CNC stands for Computer Numerical Control, and a CNC machine is a machine tool, a lathe or a milling machine or a drill, whose movements are controlled by a computer reading a program. The program is a set of numerical instructions, a list of precise coordinates and commands, and the machine follows them exactly, moving its cutting tool to the specified positions, cutting to the specified depths, producing a part that matches the program design to within a tiny fraction of a millimeter. Load a fresh piece of metal, run the program, and out comes a finished part, identical to the last one and the next one. Because the computer follows the same numerical instructions every single time, without variation, without fatigue, without skill on the part of the operator. This is how the modern world makes millions of identical precision parts. The precision and the repeatability live in the program and the computer-controlled machine, not in the human being. An unskilled operator can run a CNC machine and produce perfect parts, because the operator is not making the part, the program is. And this is precisely what makes 1942 such a puzzle, because in 1942, none of this existed. There was no computer to hold the program. There was no numerical control to guide the tool. Every machine on the factory floor had to be guided, ultimately, by physical means, by mechanical hardware, and human hands. And yet the demand was exactly the same as it is today. Millions of identical parts, to high precision, made by unskilled workers. America faced the CNC problem, the problem of mass-producing identical precision parts with an unskilled workforce, decades before CNC existed to solve it. And it solved that problem anyway, with a set of technologies and ideas so effective that they had already been perfected generations earlier, and that remain, underneath the computers, the foundation of manufacturing to this day. Here is the paradox at the heart of the story. You might assume that making precision parts requires skilled machinists, craftsmen who have spent years learning to read a drawing, set up a machine, and cut metal to fine tolerances by feel and judgment. And for centuries, that was true. A precision metal part was the product of a skilled craftsman, and the number of precision parts you could make was limited by the number of skilled craftsmen you had. But America in 1942 did something that seems, on its face, impossible. It produced more precision parts than any nation in history, to tolerances as fine as anyone's, using a workforce that was less skilled than ever before, made up overwhelmingly of people who had never touched a machine tool. It did not solve the problem of mass production by training more craftsmen. It solved it by needing fewer craftsmen, by building factories that could turn out precision parts with almost no craftsmen on the floor at all. The resolution of the paradox is the single most important idea in the history of manufacturing, and it is this. You do not have to put the skill in the worker. You can put the skill in the tooling. Instead of a skilled machinist who knows how to guide a cutting tool to exactly the right place, you build a device, a jig, that physically guides the tool to exactly the right place, so that even an unskilled worker cannot put it in the wrong place. Instead of a craftsman who knows how to hold and position the workpiece correctly, you build a fixture that holds the workpiece in exactly the right position automatically, every time. Instead of an expert who can judge whether a finished part is accurate, you hand the worker a gauge that instantly shows whether the part is good or bad. The knowledge, the judgment, the skill, all of it is designed into the physical tooling in advance by a small number of highly skilled tool makers, and then embodied in steel, so that it can be used by an unlimited number of unskilled workers. The skill is not in the hands at the machine. It is in the machine and in the jigs and fixtures and gauges around it. This is how America made millions of identical parts without CNC. It encoded the program not in a computer, but in physical hardware, and it did so long before the computer existed. The popular history of American war production celebrates the output, the astonishing numbers, the 300,000 aircraft, the 100,000 tanks, the 60,000 ships, the rivers of guns and shells and engines. It celebrates the assembly lines and the great plants and the arsenal of democracy. What it almost never explains is how, at the level of the individual part, this was actually possible. How a nation could take millions of untrained civilians and have them produce, within weeks, precision components accurate enough to be freely interchangeable. It treats the precision as a given, as if the part simply appeared, when in fact the ability to mass-produce interchangeable precision parts with unskilled labor was itself a profound and hard-won technology, arguably the deepest technology America possessed, deeper than any single weapon. And the popular history misses that this technology was not invented for the war. It was already more than a century old when the war began, developed and refined across generations, in the armories and the clock factories and the sewing machine works and the automobile plants of America, to the point where it was so mature, so completely mastered, that it could be scaled up to the demands of total war almost effortlessly. The story of how America made millions of identical parts without CNC is the story of this technology, the American system of manufacturing, the system of jigs and fixtures and gauges that put the skill in the tooling rather than the worker. It is the story of the specific mechanical devices that did the work a computer does today, and of the people who created them. And it is, in the end, the story of the single greatest industrial advantage America possessed, the one that underlay all the others, the ability to make anything, in any quantity, with whatever workforce was at hand. Let us start with the most fundamental of the devices that put the skill in the tooling, the jig, because understanding exactly how a jig works is understanding the whole principle in miniature. Imagine the simplest precision operation, drilling a hole in a piece of metal at an exact location. A skilled machinist could do this by carefully measuring, marking the spot, and guiding the drill by eye and hand to hit the mark precisely. But this requires skill. It is slow, and every part will be very slightly different because no human hand is perfectly consistent. Now imagine you want an unskilled worker to drill that same hole in exactly the same place in 10,000 identical parts. You cannot rely on measurement and judgment because the worker has neither the skill nor the time. So you build a jig. A drill jig is a device, usually a steel plate or box, that clamps onto the workpiece and has a hardened steel bushing, a precisely located guide hole, exactly where the hole in the part needs to go. The worker places the metal in the jig, and the jig holds it in the correct position. Then the worker brings the drill down, and the drill passes through the bushing, which guides it to precisely the right spot, at precisely the right angle. The worker does not have to measure anything, does not have to aim, does not have to judge. The jig physically forces the drill to go where it must go. It is not possible, with the jig in place, to drill the hole in the wrong location because the bushing will not allow the drill anywhere else. The skill of locating the hole, which once lived in the machinist's trained eye and hand, now lives in the steel bushing of the jig, located there once, precisely, by a skilled tool maker, and then used thousands of times by unskilled hands. Every hole is identical, because every hole is guided by the same bushing. This is the essence of the jig, a device that guides the cutting tool so that the operator's lack of skill simply does not matter. And the same principle extends to every cutting operation, milling, boring, reaming, each with its own jigs that guide the tool along the correct path, making the correct cut inevitable and the incorrect cut impossible. The jig guides the tool, but there is a second, equally essential half of the problem, which is holding the workpiece itself in exactly the right position, and this is the job of the fixture. A cutting operation involves two things, the tool and the work, and both have to be positioned precisely relative to each other. The jig takes care of the tool, the fixture takes care of the work. A fixture is a device that holds the workpiece firmly in one exact, repeatable position, so that every part presented to the cutting tool is held in precisely the same place and orientation as every other part. Without a fixture, a worker would have to position each rough piece of metal by hand, aligning it correctly before machining, a task requiring skill and time and prone to error. With a fixture, the worker simply drops the piece into the fixture, which locates it automatically against precisely placed stops and clamps it firmly, and now the part is in exactly the right position, guaranteed, without any judgment on the worker's part. The power of the fixture is repeatability, because the fixture holds every part in the identical position, and the jig guides the tool along the identical path. The combination produces identical results, part after part after part. The rough casting or forging that a worker loads into the fixture might vary slightly from the last one, but the fixture references it to the same locating points and holds it the same way, so that when the tool does its work, the finished dimensions come out the same. Ford's engineers had a revealing nickname for their jigs and fixtures. They called them farmers' tools because they allowed workers straight off the farm with no craft background at all to produce high-quality precision parts, doing away with the need for skilled machinists and the whole slow, expensive craft culture that skilled machinists represented. The name captured the entire philosophy. The jigs and fixtures were tools designed so that a farmer could use them to make an aircraft engine part as accurately as a master machinist, because all the accuracy was built into the tool in advance. The worker supplied only the muscle and the loading. The fixture supplied the precision. Making the part is only half the battle. The other half is knowing, quickly and certainly, whether the part you made is correct, whether it falls within the tiny range of acceptable dimensions that will let it interchange freely with all the others. And here the American system relied on a device just as important as the jig and the fixture, the gauge. In particular, it relied on the go-no-go gauge, one of the most elegant inspection tools ever devised, because it turns the difficult, skilled task of precise measurement into an instant, foolproof, unskilled check. A precision measurement done with a micrometer or similar instrument requires skill to perform accurately and time to read. You cannot ask an unskilled worker to precisely measure every one of 10,000 parts. But you can ask them to use a go-no-go gauge, and anyone can use it perfectly with no training at all. Here is how a go-no-go gauge works, and it is beautifully simple. A part must fall within a range, not smaller than a minimum dimension, not larger than a maximum. The gauge has two elements, a go element and a no-go element. Take a hole that must be within a certain size range. The go-no-go gauge for it is a steel plug with two ends. The go end is machined to the minimum acceptable diameter and the no-go end to the maximum acceptable diameter. The worker tries to insert the go end. It must fit, it must go, confirming the hole is at least the minimum size. Then the worker tries the no-go end. It must not fit, it must not go, confirming the hole is no larger than the maximum. If the go end goes and the no-go end does not, the part is within tolerance, guaranteed, and the worker knows instantly, by feel, with no measurement and no skill. If the go end will not go, the hole is too small. If the no-go end goes in, the hole is too large. Either way, the part is rejected. The entire complex question of whether a part is within precise tolerance is reduced to two simple physical tests that any worker can perform in seconds. Does it go? Does it not go? The judgment of the skilled inspector, like the skill of the machinist, has been designed into a piece of steel. Multiply this across every dimension of every part, and you have a system in which interchangeability is verified constantly, instantly, and by anyone without a single precision measurement being made on the floor. But all of this precision, the jigs and the fixtures and the gauges, rests on a deeper foundation because it raises a question. If a gauge defines what is correct, then what defines the gauge? How do you make the gauges themselves accurate? And how do you ensure that a gauge in a factory in Detroit measures exactly the same as a gauge in a factory in California, so that parts made in both places will interchange? The answer lies in one of the most important and least celebrated inventions in the history of precision manufacturing, the gauge block, and in the Swedish immigrant who perfected it, Carl Edvard Johansson. Gauge blocks, often called Joe blocks in his honor, are small, precisely finished blocks of hardened steel, each one manufactured to an exact thickness with an accuracy measured in millionths of an inch. They are the physical embodiment of precise length, the master standards against which everything else is measured. The genius of Johansson's gauge blocks was twofold. First, he manufactured them to an unprecedented degree of accuracy, so that a gauge block was a reliable physical standard of length far finer than anything most factories had possessed before. Second, and remarkably, he designed them as a set of graded sizes that could be stacked together and finish their surfaces so precisely flat and smooth that when two blocks were pressed together, they adhered to one another, a phenomenon called ringing, forming a combined stack whose total length was the exact sum of the individual blocks, accurate to millionths of an inch. With a single set of gauge blocks, a factory could assemble a precise physical standard of almost any dimension it needed and use it to check and calibrate all its gauges and instruments. These master standards were the anchor of the entire system. The gauge blocks calibrated the gauges checked the parts, and because the gauge blocks were traceable to a common standard, parts made in different factories, checked against gauges calibrated to the same gauge blocks, would interchange. Johansson's precision blocks were the invisible foundation beneath the whole edifice of interchangeable manufacturing, the ultimate physical reference that made it possible for millions of parts made in hundreds of factories to all agree on what an inch was, to millionths of that inch. So far, we have described how an unskilled worker, aided by jigs and fixtures and gauges, could make precision parts. But the most striking anticipation of CNC in the pre-computer age was a machine that removed even the worker from the cutting, a machine that produced finished precision parts automatically, one after another, from raw bar stock, with almost no human intervention at all. This was the automatic screw machine, and it was, in the most literal sense, a machine that ran a program decades before the computer, with the program embodied not in code, but in metal. The automatic screw machine was a lathe, a machine that shapes metal by rotating it against cutting tools, but an automatic one whose entire sequence of operations was controlled by cams. Here is how it worked, and it is a beautiful piece of mechanical thinking. A cam is a specially shaped disc or drum, and as it rotates, its changing profile pushes on a follower, converting the cam's rotation into a precise, timed motion of some part of the machine. In an automatic screw machine, a whole set of cams was mounted on a camshaft, and as the camshaft turned, the cams drove the machine's every action in a precise, repeating sequence, feeding a length of metal bar forward, bringing the cutting tools in to turn and shape and cut it, drilling, threading, forming, and finally cutting off the finished part, whereupon the cycle began again. The shape of the cams was the program. A skilled toolmaker designed and cut the cams so that their profiles acting through the followers would drive the tools through exactly the right sequence of motions to produce the desired part. Once the cams were made and installed, the machine ran automatically, producing a stream of identical parts from bar stock, part after part after part, with an operator doing little more than keeping it fed with bar and supplied with coolant, and clearing away the finished pieces. The cams held the program, the way a computer file holds a CNC program today, and the machine executed it tirelessly. Change the cams, and you change the part the machine made, exactly as changing the program changes what a CNC machine makes. The automatic screw machine was the mechanical ancestor of CNC, a programmable automatic machine tool whose program was written in the shape of steel cams, and it poured out the small precision-turned parts, the screws and pins and bushings and fittings that a mechanized war consumed by the billion. The jig, the fixture, and the cam handled parts of relatively simple geometry, but the war also demanded parts of complex, curved, three-dimensional shape, the contours of a propeller blade, the intricate cavity of a die, the sculpted form of a cam itself or a turbine component. How do you mass-produce a complex three-dimensional shape without a computer to guide the cutter through its curves? The answer was another ingenious pre-computer technology, the tracer machine, also called a copying machine, and it was perhaps the closest of all to what CNC would later become, because it followed a master pattern to reproduce a shape automatically. A tracer machine worked by following a model. You would make one master pattern, a perfect example of the complex shape you wanted to reproduce, crafted with great care by a skilled pattern maker. Then, on the tracer machine, a stylus, a tracing finger, was run over the surface of that master pattern, following all its contours and curves. As the stylus moved over the master, its movements were transmitted through mechanical linkages, or more powerfully, through hydraulic servo systems, to the cutting tool, which moved in exact correspondence over a piece of raw metal, reproducing on the workpiece every contour the stylus traced on the master. The stylus followed the master's curves, and the cutter carved those same curves into the new part. In effect, the master pattern was the program, a physical, three-dimensional program, and the tracer machine read it not with a computer, but with a stylus, and executed it, not from numerical coordinates, but from direct physical correspondence. With a tracer machine and one master pattern, a factory could reproduce a complex shape over and over, each copy faithful to the master, mass-producing intricate three-dimensional forms that no jig or simple fixture could have handled. The tracer was the true mechanical forerunner of CNC, differing from it in one essential respect, that where CNC follows a program of numbers stored in a computer, the tracer followed a program embodied in a physical master pattern read by a mechanical finger. The idea was identical. Only the medium of the program was different, steel and hydraulics instead of silicon and code. None of this was invented for the Second World War. The entire system, the jigs, the fixtures, the gauges, the principle of putting the skill in the tooling, was more than a century old by 1942, and understanding where it came from reveals why America, of all nations, was so supremely good at it. The system was born, appropriately enough, in the manufacture of weapons, in the national armories of the young United States, at Springfield in Massachusetts and Harper's Ferry in Virginia, in the early decades of the 19th century. It came to be known, in fact, as armory practice, because it was in these government arms factories that the techniques of interchangeable manufacturing were first systematically developed and perfected so completely that the American system of manufacturing became known around the world as the distinctively American way of making things. The goal at the armories was interchangeable muskets, weapons whose parts were made so uniformly that the lock from any musket would fit any other, so that broken weapons could be repaired in the field by swapping parts rather than by hand-fitting new ones. This was a revolutionary and difficult goal, and it drove the development of exactly the technologies we have described, the jigs to guide the tools, the fixtures to hold the work, and above all, the gauges to verify uniformity. A great deal of credit belongs to a figure named John Hall, who at Harper's Ferry in the 1820s pursued what was called the uniformity principle with unusual rigor, building a system of machines, jigs, fixtures, and gauges that could actually achieve interchangeability in a complex mechanism, the rifle, to a degree that had eluded earlier efforts. Honesty requires noting that the popular story crediting Eli Whitney with inventing interchangeable parts through a famous 1801 demonstration for government officials is largely a myth. His demonstration was partly staged, and his own production never achieved true interchangeability. The real achievement was collective and gradual, the work of the armories and of dedicated men like Hall over decades. But the result was real and world-changing. By the middle of the 19th century, American factories were making interchangeable parts by armory practice, and the technique spread from guns to clocks to sewing machines to bicycles, and eventually to the automobile, growing more refined at every step. If the armories created the system, it was in the automobile industry that it reached the scale and precision that would define the 20th century. And the man who did more than almost anyone to bring true interchangeable precision to the automobile was Henry Leland, a figure who connects the whole story together. Leland was a machinist and a precision man to his bones, and crucially, he had learned his trade in exactly the right place, in the New England precision industries, including the arms industry, at firms like Colt and Brown and Sharp, the very heartland of armory practice and precision gauging. He carried that gospel of precision and interchangeability out of the arms and machine tool world and into the young crude automobile industry, where standards of precision were, at the time, far lower. Leland founded Cadillac, and he built it on the principle of precision interchangeable parts, applying the armory tradition to the motor car with a rigor no one else in the industry matched. And in 1908, he arranged a demonstration that proved dramatically and publicly what interchangeability meant, in a test conducted in England for the Royal Automobile Club. 3 Cadillac cars were taken, and they were completely disassembled, broken down into their component parts. The parts were then mixed together, scrambled, and some were replaced with parts taken from dealer stock. And then, from this jumbled pile of interchangeable components, 3 cars were reassembled using only wrenches and screwdrivers, No filing, no fitting, no adjustment, and all three ran perfectly and were driven around a track for hundreds of miles without trouble. For this demonstration, Cadillac was awarded the Dewar Trophy, the most prestigious award in the automobile world, and Leland earned a reputation as the master of precision. The 1908 test was the armory principle made visible, the proof that parts could be made so uniform that they were freely interchangeable, and it was the foundation on which the entire mass production automobile industry and later the entire war production machine would be built. Alfred Sloan, who ran General Motors, considered Leland one of those chiefly responsible for bringing interchangeable parts into automobile manufacturing. And the automobile industry Leland helped shape was, when the war came, exactly the industry that would convert its plants to war production and pour out the interchangeable parts of victory. Now we can see the full picture of how America made millions of identical parts without CNC and appreciate its most profound consequence, which was about people. Because the skill lived in the tooling, the jigs and fixtures and gauges and cams, rather than in the worker, America could take a workforce with almost no industrial skill and put it to work making precision parts almost immediately. This was not a minor convenience. It was one of the decisive facts of the entire war. When America mobilized, it pulled its skilled men into the armed forces by the millions, stripping the factories of exactly the experienced workers who, in an earlier age, would have been essential to precision manufacturing. And it replaced them with people who had never worked in a factory, above all, with women, the legendary Rosie the Riveter and her millions of sisters, who poured into the war plants and, within weeks of training, were producing precision components to aircraft tolerances. This was possible only because of the system. A woman who had never seen a machine tool did not need years of apprenticeship because she was not being asked to supply the skill. The skill was in the jig that guided her drill, in the fixture that held her work, in the gauge that checked her part, in the cams that ran her automatic machine. She needed to learn only the simple physical routine of her particular operation: load, actuate, unload, check, and the tooling did the rest. Samuel Colt, the arms manufacturer, had said, with brutal frankness, generations earlier, that the more ignorant a man was, the more brains he had for Colt's purpose, meaning that a worker with no preconceptions and no craft pride would simply do the simple task the system required without trying to apply judgment the system did not want. It was a cold way to put it, but it captured the reality that the system was designed to extract precision from unskilled labor, and that this was its supreme strength. In the war, this strength became a weapon. America could mobilize its entire population, skilled or not, into precision war production, because its manufacturing system had, over a century, been designed precisely so that skill was not required of the worker. The nation's whole labor force, including tens of millions who had never made anything, became a precision manufacturing workforce almost overnight, and out of their hands, guided by the tooling, flowed the interchangeable parts of the arsenal of democracy. The results of this system applied to total war were simply staggering, beyond anything any other nation approached. America produced in a few years some 300,000 military aircraft, over 100,000 tanks and armored vehicles, over 2 million military trucks, millions of machine guns and artillery pieces, and tens of billions of rounds of ammunition. Every one of these was an assembly of interchangeable precision parts, and every one of those parts, and there were trillions of them, had to be made to tolerance and made to interchange. The sheer number of individual precision parts that American industry produced during the war is beyond real comprehension. And it was all done without a single computer-controlled machine, by the system of physical tooling we have described, operated by a largely unskilled workforce. The precision was maintained not by computers, but by jigs and fixtures and gauges and cams and tracers and gauge blocks, by the accumulated genius of a century of armory practice, embodied in steel and deployed at continental scale. This was the true arsenal of democracy, not merely the quantity of weapons, but the manufacturing system that could produce that quantity to the required precision with the workforce available. Other nations had brave soldiers and clever engineers, and even, in some cases, superior individual weapons. What America had more than any other nation was the perfected ability to make anything in any quantity to precision, with whatever hands were available. It was the deepest industrial advantage in the world, and it was decisive. The contrast with Germany illuminates the American achievement, because Germany, for all its engineering genius, never fully embraced the American system, and it cost them. German manufacturing was rooted in a deep and proud craft tradition, in the skilled machinist and the master craftsman, the Meister who had spent years mastering his trade. German engineering culture valued the skilled worker and the finely made, individually fitted product, and German factories relied more heavily on skilled labor and on the judgment and craftsmanship of experienced workers than American factories did. In peacetime and for producing small quantities of superb equipment, this craft tradition produced magnificent results, some of the finest engineered products in the world. But in the context of total war, the craft tradition was a weakness where the American system was a strength. German production depended on skilled workers who took years to train and who could not be quickly replaced, and much German equipment was made with a degree of hand-fitting that made it slow to produce and hard to repair with interchangeable parts. When Germany needed to mass produce, it struggled to match the American ability to pour out interchangeable parts with unskilled labor, because it had not developed the system to nearly the same degree, and because its whole industrial culture was oriented toward the skilled craftsman rather than the de-skilled, tooling-driven production line. American equipment was often less finely finished than German equipment, its parts made to a tolerance rather than lovingly hand-fitted, but American equipment could be made in enormous quantities by anyone and repaired in the field by swapping parts, and that mattered more. The German craftsman made a superb part slowly. The American system made a good enough part by the million with unskilled hands, and in a war of mass production, the million good enough parts, interchangeable and endlessly replaceable, beat the superb hand-fitted part every time. Germany's craft tradition, its very excellence, held it back, while America's de-skilled, tooling-driven system, which put the skill in the machine rather than the worker, let it outproduce the world. The lesson of this story reaches beyond the war, into the deepest nature of what manufacturing is and how industrial power is created. The central insight that skill can be moved from the worker into the tooling, from the hand into the jig and the gauge and the cam, is one of the most powerful ideas humanity has ever had, because it breaks the ancient link between the number of skilled craftsmen and the number of precise objects that can be made. For most of human history, if you wanted more precise objects, you needed more skilled craftsmen, and skilled craftsmen took years to make. The American system broke that limit. By investing skill once in the design of the tooling, it could then produce unlimited precise objects with unlimited unskilled labor. The bottleneck of craftsmanship was removed. Precision became scalable. This is why America could become the arsenal of democracy, and it points to a truth that runs through the whole history of industry, that the deepest advantage is often not in the product, but in the ability to make the product, not in the design of the weapon, but in the system that can produce it by the million. America did not necessarily design the best individual weapons of the war. What it possessed supremely was the system to make weapons, any weapons, in overwhelming quantity to sufficient precision with whatever workforce it had. The skill was in the steel, in the jigs and fixtures and gauges, in the accumulated wisdom of a century of putting the program into the tooling. And that, more than any single machine or weapon, was how a nation of untrained civilians made the millions of identical precision parts that won the war without a single computer to guide their hands. In a war decided by what could be made, and how much and by whom, America made the impossible ordinary. It took millions of people who had never touched a machine, and within weeks it had them producing precision parts accurate to thousandths of an inch, freely interchangeable across a continent of factories, in quantities the world had never seen. It did this with no computers, no numerical control, none of the technology we now consider essential to precision mass production, because it had something older and, for its time, just as powerful. It had learned, over a century of armory practice and automobile manufacturing, how to take the skill out of the worker and build it into the tool. The program that a computer holds today, America held in steel, in the hardened bushing of a jig that guided the drill to the only place it could go, in the clamps of a fixture that held every part identically, in the two ends of a gauge that told any worker instantly whether a part was good, in the shaped cams of an automatic machine that ran their program tirelessly, in the master pattern that a tracer's finger followed to carve 1,000 identical curves. The skill was in the steel, placed there once by a small number of brilliant toolmakers, and then used 1 billion times by hands that needed no skill at all. This was the true arsenal of democracy, not the quantity of weapons alone, but the system beneath the quantity, the de-skilled, tooling-driven, gauge-verified system of interchangeable manufacturing that let a whole nation, skilled and unskilled alike, become a precision workforce overnight. Germany kept its faith in the master craftsman and made superb things slowly. America put its faith in the jig and the gauge and made good enough things by the million with anyone's hands, and the million beat the superb. In a war fought between industrial systems, the system that could make millions of identical precision parts without a single skilled worker at the machine, without a single computer at the controls, by the sheer accumulated genius of a century of putting the program into the tooling, was a system no enemy could match. The computer would come later, and the numerical control, and eventually the CNC machine that reads a digital program and cuts to millionths. But in 1942, before any of that existed, America had already solved the problem the CNC machine would later solve, and solved it in steel. It had discovered generations earlier that you do not need to put the skill in the worker if you put the skill in the tool. And on that single idea, embodied in 100 million jigs and fixtures and gauges, it built the greatest production of precision goods in the history of the world, and made the parts that won the war. There were no CNC machines in 1942. There did not need to be. The program was written in steel, and it ran flawlessly 1 billion times over in the hands of a nation that had learned long before how to make anything. That was enough. In a war decided by what could be made, America could make anything, and did.